Now I'm going to be explaining the algorithm of BYOL for contrastive learning. So they introduced bootstrap your own latent, a new approach to self-supervised image representation learning. BYOL relies on two neural networks referred to as online and target networks that interact and learn from each other. From an augmented view of an image, we train the online network to predict the target network representation of the same image under a different augmented view. At the same time, we update the target network with a slow-moving average of the online network. BYOL does not collapse, and it is more robust to the choice of image augmentation than contrastive methods. We suspect that not relying on negative pairs is one of the leading reasons for its improved robustness. Previous methods based on bootstrapping have used pseudo-labels, cluster indices, or a handful of labels. We propose to directly bootstrap a representation. So starting from an augmented view of an image, BYOL algorithm trains its online network to predict the target network's representation of another augmented view of the same image. Many successful self-supervised learning approaches build upon the cross-view application, and typically these approaches learn representations by predicting different views of the same image from one another. Many such approaches cast the prediction problem directly in representation space. Predicting directly in representation space can lead to collapsed representations. For instance, a representation that is constant across views is always fully predictive of itself. Contrastive methods circumvent this problem by reformulating the prediction problem into one of the discrimination. From the representation of an augmented view, they learn to discriminate between the representation of another view of the same image. So we just task ourselves to find whatever these negative examples are indispensable to prevent collapse while preserving high performance. This is the architecture this is called the online path, the online network, and we have another path. They are the same, completely similar to each other, except the last network, which is the prediction, but the target one doesn't have prediction. And we want the online path to be as close as possible to the target paths. Given a target decay rate tau, now after each training step, we just update with this moving average. And in their original formulation, they use this loss, but in the appendix, they also try to symmetrize this loss, because Q is coming from predictor and Z prime is from the target. So the online is updating, so this one is using backpropagation, but this one is just using a moving average in order to reduce those high frequency variations. So implementing it is just a linear combination of your old weights and the new weights. So typically it's about 95%. While BYOL does not use an explicit term to prevent collapse, and it may seem that BYOL should converge to a minimum of this loss. While BYOL dynamics still admit undesirable equilibria, we did not observe convergence to such equilibrium. and the hypothesis that undesirable equilibria are unstable. And it's an ablation through contrastive methods, because we recast SimCLR that I've explained in another video with BYOL using the same formalism to better understand this. And this is the info NCE, and S here is just a normalized dot product. So we first sample a batch of n images, and then we do sample image transformations because we need different views, different augmentation, and then we have a projection layer. Then we can compute the target projection, and the loss in one of the slides was just one of them, but at the implementation, if you look at their GitHub page, you will see that they also add another term in order to make it more symmetric. And finally, for the target of parameters, it's just a linear combination of old weights with the new weights. So we use moving average because we care about it's just 95% of the old weights with the 5% of the new weights. And this is the normalized version of dot product between the target prediction, the online prediction, and the target output. So in the target path, we are missing this extra prediction model. So the architecture are designed to be asymmetric. Otherwise, it would collapse. So there are two reasons that this network does not collapse. One of them is exponential moving average. The other one is asymmetric architecture of this design. As you see, it is missing the prediction layer.